Hello student, welcome to our physics discussion, that is physics in a smart way. Today we shall be discussing current electricity. In the series of our lectures in current electricity that you might have gone through, we started with electric current, then we have gone into network analysis or circuit theory. The foremost rules there were Kirchhoff's rule, the most fundamental rules, and we have discussed, after discussing Kirchhoff's law, the Kirchhoff's current law, that is KCL, and Kirchhoff's voltage law, that is KVL. We have discussed the pros and cons of it, and so far as cons part is concerned, the deficiencies in Kirchhoff's law, as you know, we cannot avoid Kirchhoff's law. They are the most fundamental principles. But if somehow the deficiencies can be overcome, or somehow we know how to circumvent it, then we make ourselves a bit more powerful. So in that discussion, we had gone into Kirchhoff's open path voltage equation analysis, where original KVL won't do the things. How to take, there we have discussed how to take an open path where current is flowing. If it is a capacitive network, then current may not flow. Still then we'll be able to find the potential difference in a circuit where, or in a path where the starting and ending points are different. So in the same series, continuing with that idea, we consider another idea which I am borrowing from a network theorem that is known as nodal analysis. Nodal analysis. In fact, the original theorem is quite elaborate. I won't be taking that. I shall be considering only the portion which is useful to you. Everybody knows node, we may say joint, we may say junction. They all mean the same thing, where for our purpose, so far as a 12th student is concerned, the number of conductors, they meet at a point, and number of conductors should not be less than 3. Then we say that is appropriate. It is a node or a joint or a junction. So that is junction-based analysis, and stress is given to the potential difference again. Okay. So we start with the idea, but I am simplifying it in my own way. Let us say we consider case 1. In that case, we have been shown a circuit. In fact, it is not a circuit in the true sense, only a resistor where a current is flowing, current equal to I. The ends of the resistor are A and B. As you can clearly see, this resistor must be the part of a big network or part of a network, because current flows only in a closed path, and somehow A must be connected to something or somebody, B must be connected to something. We are not shown the diagram of those. And only this much portion of the network is given. And here I remind you another important theorem in current electricity that is very well known, that is Ohm's law. Ohm's law, which says current in a network or current in a resistor must be equal to potential difference across it by the resistor. If you apply Ohm's law in our case, we know because the current is flowing from left to right, that is the conventional current. So point A or the end A must be at the higher potential end compared to end B. So the potential difference should be mentioned as VA minus VB by R. In short, we can write as VAB by R. Here, VAB means we are just making our writing short. That is VA minus VB. Okay? And you understand it perfectly well because you are very much conversant with Ohm's law. If you are in class 12, you have known it since your school level, and you know how it works and what are the terms involved in it and what they mean. Now, let us make our case slightly complicated. Just like the last case, we got a similar portion of a network and A, then you got a resistor, then you got a cell or a battery, then you got NB, then you got NB, and current is given or maybe assumed, doesn't matter. Current is flowing from A to B. The battery has got a EMF. EMF of the battery is E. Again, you are asked to use Ohm's law and to find out current or to write the so-called expression for the current. So we start writing the current. I will be equal to, you know, the current in a particular branch, in a particular path, it always depends upon the end potential difference. So that must depend upon VAB. But we know at the same time, another mischief maker is coming in. That is the battery. Battery creates a potential difference and that will cause complication. Okay. And here battery potential must be accommodated because battery creates a potential difference. So along with VAB, as our common sense says, if we use our logic or common sense, the battery potential must be accommodated. But we do not know whether the battery potential will be helping the battery EMF. EMF will be helping the current or opposing the current. So thereby, we'll be confused to write whether it is VAB plus E or VAB minus C by R. We know at best we can write like this. To decide whether it is a plus or minus, let us say, we consider a thing like this. Say temporarily we forget VAB and the current is flowing. We know circuit must be closed. Circuit must be closed. If the battery or the cell would have been the sole controller of the circuit, then battery must have made its own current to flow. We forget VAB. And we know circuit must be closed. Somehow it must be closed. Otherwise, current doesn't flow in an open path. If battery would have been the most dominant, the potential difference maker, so to say, in the circuit, then battery must have made the current to flow in its own way. And how a battery, if the ends are connected, how a battery makes its own current to flow? We know the battery's current always comes out of the battery's positive. That is battery positive, that is battery negative. If the ends of the battery is connected, maybe by some circuit elements or maybe directly is a bit risky. It can create a huge current and all that. But always the own current of the battery or the current driven by the battery will be coming out of the battery positive. So here in this circuit, if battery would have been the dominant or the most powerful element which makes the current to flow, then battery would have created the current which would have come out of the battery positive. We compare that imaginary current driven by the battery with the main current that is given. We know the current directions are opposite, and we know here battery must be in a negative role. Battery must be in a negative role. So here our answer will be BAB minus E. I am writing it more legibly. That must be BAB minus E by R. And BAB always means that is BA minus VB. I think I am clear. Okay, we now take another case, that is case 3, where a full-fledged branch is shown to you. There are three registers, 2 batteries are there, and it may be that the current is actually flowing from A to B, or you have assumed the current to be flowing from A to B. Mark my words, you may assume also, but your assumption and further statements, they must support your assumption. And here we have to write the current equation, again following the same Ohm's law. So you know current basically depends upon N potential difference. So first of all, we write VAB, that is VA minus VB, already you know. We'll take the fast battery. So far as the fast battery is concerned, we know if the fast battery is given the freedom, fast cell is given the freedom, if it is the sole decision maker, so far as the current flow is concerned, that would have made the current to flow, and that its current would have come out of its positive terminal. So that current, that imaginary current, that fast battery would have made it to flow, that matches with our main current I, both are in the same direction. So now you know the fast battery is in a positive role, that is plus E1. Now you go down to the second battery. Second battery's current will be opposite, because second battery's, if second battery or second cell is given the freedom to make the decision on the current flow, then its current would have come out of its positive. So that current is opposing our main current. So now you know the second battery is in opposite role or negative role. So that is the net potential difference divided by the resistance. When you write resistance, keep in mind in a path or remains a single path, of course, that is against the spirit of English, but it doesn't matter. We don't bother, because here science matters. In a path or in a single path, if you find some resistances, assume them to be in series, because you know the main criteria of a series combination of some resistances, maybe some capacitances, same current passes through all of them. So whatever resistances you are having, They are all in series. So we try to find the net resistance across A and B. That will be R1 plus R2 plus R3. Keep this in mind always. In a single path, whatever the resistors they are there, they are in series. The same thing is valid for capacitors. If you try to find if the resistors are replaced by capacitors, if you try to find the equivalent capacitance or effective capacitance across A and B, you would have taken C1, C2 and C3 in series. So the total resistance across A and B will be R1 plus R2 plus R3. So that is the way we write the current expression. You may have realized or not, in fact, we have acquired the strength. If you have understood me till this point, we have acquired the strength to find out the current in a branch by a single equation which is written in this way. We now try to apply this in a practical circuit. Of course, our circuit here given is also practical, but here the things are in symbols where I would like to take a circuit where things are given in numbers and we try to find some answer. We cannot find a better example than a circuit of medium level, and such type of circuit we had considered in our last video when we have established Kirchhoff's open path voltage equation, and let me consider that that type of circuit. So I am clearing the drawing. Let us consider a circuit. The point A, then there is a resistance. Let us say R1 equal to 3 ampere, 3 ohms, sorry. Current is flowing. Let us say that is 2 ampere. There is a battery here E1 equal to 5 volt. Let us say there is another resistor, say R2 equal to 1 ohm. There is a joint O. Okay, there are two paths which start out from O. If you go to the right, there is a third resistor R3 equal to 2 ohms. Then there is another battery E2. I am writing E2 equal to 2 volt. Then that is the end in our diagram. But the circuit doesn't end here. The diagram ends there. Then there is some battery, there is some resistance in this path. Let us say that is R4. R4 equal to 5 ohm. And there is a battery or cell that is E3. E3 equal to, let us say 4 volt. There may be some other resistance. And that is the NC. Let us say that is R4. R4 equal to, say, that is 6 ohms. The currents are given. Here the current in this path is given to be, let us say, 1 ampere. In this path, that is 1 ampere. And here the question for us, the question says, find the potential difference. Find the potential difference in between the points A and B. That is the question. So just like we have done there, we got a similar situation here, a circuit or the portion of a network. We know A must be connected to something at the left-hand side, B must be connected to something. Similarly, C must be connected. Otherwise, how can the current will flow? But we have shown the portion of a network. The portion of a network, and the current in the path AO is given to be 2 ampere. The current in the path CO is given to be 1 ampere. Just like you have done here, just like you have done there, your job is to find the current in the path OB, and that current can be easily find out if you remember the Kirchhoff's current law, and the joint O, sum total of current coming to it must be equal to sum total of current going out of it. So you know the current in the path OB must be equal to 3 ampere, and that is going from O to B, because it is 2 ampere coming in and 1 ampere coming in to the joint O, and only one path is remaining, that is OB, and the current equal to 3 ampere. There, our procedure was slightly different. After establishing current in the path, we used to give proper plus minus signs showing the resistors with high potential and low potential ends, then batteries and all that. Here, we do not do such. We do not do those type of things because we don't need it here. We try to solve with the principle that we have learned here, that is nodal analysis. Nodal analysis. One defect with, if you consider the pros and cons, one defect with the nodal analysis is that it can be readily used, readily applied to a branch, but it cannot be made to go beyond a branch. In that way, we can use nodal analysis for the branch AO, or maybe the branch BO or OB, maybe the branch OC, but I cannot use nodal analysis right away from A to B, because the potential difference in between A and B is asked. So already you do know, we have covered such type of question. You have to consider a path that is from A to B. But when I consider an electrical path from A to B, we know a joint is intervening, and the moment joint comes in, the branch ends there, another branch or branches they start up. So we got the branch AO, the branch OB, and the branch OC. Nodal analysis can be useful directly for the branch AO, for the branch OB, and for the branch OC. You might be wondering how I am to apply directly from A to B. The answer is that it cannot be applied directly, but that doesn't create such a big issue for us. Just our equation needs to go a step more, a step further, and that is not a big step. We can be finding out. Let us see how it can be done. So if I consider the path or the branch AO, for the path AO, whenever you are looking at AO, you just look at AO, close your eyes to the remaining things, that is OB and OC, and try to write the current, use the same old Ohm's law that you have done in the last 3 cases. In the path AO, the current equal to 2 ampere. So current, maybe I1, that is 2 ampere. That must be equal to V net potential difference, by the resistance you are having. The net potential difference will be controlled by the end potential difference, that is VAO. VAO, because the branch is from A to O. And then the battery is there. Battery's own current, as you have learned it, will be opposing the 2 amperes. So thereby the battery is in a negative role. So we say that is -5. By the resistance in the circuit will be equal to, in the path AO, there are 2 resistors. One is 3, other is 1. That is 3 plus 1, that is 4. 3 plus 1, sorry. So that gives, when you cross multiply, that is 4 into 2, 8. So VAO is equal to how much? That is 13 volt. Okay, we stop there. We stop there. Next, because our intention is to start from A and go on investigating till we reach the end B, we consider another path, second path, that is path OB. In the path OB, you know the second current, that is I2. It is given to be 3 ampere, and that we write as per our nodal way. So 3 ampere current will be the end potential difference across that branch. That will be VOB. Then the battery comes in. Battery will be helping the main current because battery's own current is in the same direction as main current. So thereby battery potential or EMF will be contributing positively, that is +2. By the resistance in this path, the entire resistance in the path from O to B, that is 2 ohm. So we write by 2. So just like we did find out, cross multiplying, so VOB will be equal to 4 volt. Now you must be wondering, the writing like this or finding this quantity, to what help you will do? Our basic issue was to find out VA minus VB. Already you have found out the answer, because you know the moment we say VAO, that is equal to VA minus VO. That is given as 30. That we take as equation number 1. And the next we got VOB. VOB, that means VO minus VB. That is given as 4. We consider as equation number 2. We just add these two equations. We know when we add the LHS left hand side, VO and VO will be cancelling out. So VA minus VB will be equal to, when you add the equation 1 plus equation 2 will be giving us VA minus VO VB. Sorry, that will be 13 plus 4, that is 17 volt. I think I am clear. So thereby we see another positive sense in this, that is positivity, or maybe it's advantage for us. Unlike the original Kirchhoff's voltage law and all that, where you we fill the entire circuit by proper plus minus signs and then start to write the potential differences blindly, drops, gains, potential loss, gains, and then at last we put the right hand side to 0. And when we use the second approach that we have discussed in our last video, we start with the potential of a point and then go on taking the losses and gains of potential, and then the entire equation we at the end equate with the potential of the ending point where our imaginary charge ends. So when you compare those procedures, I would ask you to review all those videos again with the process that we have taken. We know our process is more methodical. Methodical means we got many scopes to check if there is any mistake in our calculations, and it gives you more control. It gives you more control on the issue. Okay. So anywhere one of the equations goes wrong, the entire thing is not going down to the drain. We can rectify that. Other equations will be remaining as it is, and then we can find out the end result. So thereby, nodal analysis is bit better way, especially if you are dealing with a branch and all. It's a better way to analyze. And we write the things in such a way that even if a teacher, okay, if it's somehow, I may say, hardliner, you are with NCERT, you have to follow the rules of NCERT or our CBSE books and all that, why you have gone to a, why you have gone learning a different theorem and all that. So they may not find out, anything with our approach, because we can point out, we have used the same old Ohm's law here. We have not taken anything esoteric. So thank you for your viewing. If you find it's helpful, you can like it, you may subscribe to it, and please share it amongst your friends. That will be helping you and helping me at the same time. Have a good day. Stop meeting, Helena.